Okay, continuing the last video, where are we at this point? We know that v1 of t is 1/2 a1t squared. We know that x1 of t is 1/2 a1. That's not right. Let me fix that. Okay, we know that x1 of t is 1/2 a1t squared. We've used this, setting this equal to L over 2 to find that t halfway is the square root of L over a1. So t halfway is just another quantity that we will have determined, or can have determined at any point after obtaining x1 of t. The v2 of t is a2 times t minus t halfway. And what am I doing? Hang on, I've got another mistake. I'll fix that one right before your very eyes. Okay, v of t is a1t, not 1/2 a1t squared. That's your x1 of t. Okay, so again, v1 is a1t, x1 is 1/2 a1t squared. These are obtained by integrating a1 twice and applying the initial conditions. v1 of 0 equals 0, x1 of 0 equals 0. v2 of t is a2 times t minus t halfway. That's the result that we just got. x2 of t then equals what? Well, it equals the integral of v2, an integral of v2 of t. And applying the initial conditions, we will easily obtain that this integral is, first of all, it's the integral of a2 times t minus t halfway squared, so it's going to be 1/2 a2 times t minus t halfway squared. I think I set a square up here where I didn't mean it, but anyhow, we integrate v2 of t, which is this expression, and we get this. And then we get our integration constant c. Now, what's our initial condition? x2 of t halfway, which is again a time that we couldn't easily have determined by now. We can determine it at any point. Has to equal 0. So x2 of t halfway is 0. What's this mean again? This means that at t halfway, which is when the first ball is halfway down its ramp, we release the second ball from the top of its ramp. So the x2 position at the top of the ramp is 0. That occurs when the first ball is halfway down. And then setting this equal to 0, we evaluate c. We find that c is 0. So that x2 of t is 1/2 a2 times the quantity t minus t halfway, quantity squared. Now that we have our x1 and x2 functions, we want to determine the acceleration a2. How do we do that? Well, we take what we know and we see if we can put it together and come up with an equation that we can solve for a2. One thing we know is that x1 of t final has to equal x2 of t final being the time when both of the balls get to the end of the ramp, and that common value of x1 and x2 at that instant will be L, because both balls will have traveled the length of the ramp. So t final is what we're using, of course, for the common clock time when the balls reach the end. So again, x1 of t final equals x2 of t final equals L. Now, let's take x1 of t final, which is equal to 1/2 a1 times t final squared, and set that equal to L. Is there anything here that we can't find from the information we presumably know? Well, we presumably know the length of the ramp, and we presumably know a1, the acceleration on the ramp, so we can easily solve this for t final, and you can verify that that solution, t final, is square root of 2L over a1. Now you can compare that and kind of keep that in mind with the t halfway, which is just the square root of L over a1. And so here we have the 2, here we don't. And you should think about why. You should think about how these numbers come about from the conditions that we've postulated here. Okay, so we have x2 of t final also equals L. And notice we never have really set x1 of t final equal to x2 of t final. We used the fact that x1 of t final equals L to just solve directly for t final. And now x2 of t final has to equal L. Well, what's x2 of t? Well, here's your x2 of t. We plug t final in for t, and this expression becomes this expression, the only difference being that t is replaced by t final. That's equal to L. Now, t halfway and t final are both quantities that we know in terms of the quantities that were given, the acceleration a1 and L. So this is an equation we can easily solve for a2. This is easy enough to solve. We simply multiply both sides by 2 and divide both sides by the square. And let me fix this. I wrote this down without the square on it. So I got parentheses around. There's a square there, believe it or not. This one's a little easier to see. Okay, so the solution's very straightforward. You can write that down, but of course this expression needs to be simplified, and I'm going to leave it to you to simplify and interpret this. Simply because your algebra needs just a little bit of, might need just a little bit of brushing up or maintenance, and that's a reasonably easy problem, a reasonably easy expression to simplify. It's just a little more than I'd probably want to give my college algebra class, who are into this sort of thing right now. And one last comment. I did get, I think, an answer to the question of what does the second acceleration have to be for the second ball to catch the first. I think I got maybe an answer like it ought to be twice the acceleration because it's got to go twice as far or something like that. And it was a little more complex. The reason it was a little more complex than that, I'll just say that A2, according to this, is way more than double A1. And you might or might not be surprised by the result that you get here. And that might be related to the result that sort of surprised me on your homework, although it was correct. One of the first problems where you release two balls at different times, and they went like 1,700 centimeters before the second ball caught up with the first. The accelerations were 20 and 30 centimeters per second, and I thought it was kind of interesting that they went as far as they did. I verified that, and when I saw the solution, I didn't think it would go that far. I thought maybe a few hundred, but went way further than I thought. Remember that our intuition isn't always reliable, and that if you give an answer that seems obvious without running through the mathematical analysis, you might end up way off, and you might end up, maybe crashing your spacecraft into Mars or something.